Thank you, everyone. Thank you, Megan. Thank you, organizers. Thank you, attendees. I'm happy to be able to present to you Speckle Observations of Near-Earth Asteroids. Here's a list of my co-authors there. Let me briefly tell you about near-Earth asteroids, and then I'll tell you about some Gemini observations, of course. Near-Earth asteroids are bodies whose orbits bring them close to the Earth's orbit. It is interesting and important to study them both for reasons of science and also planetary defense. I'm showing you three pictures here. On the upper right and the lower left are pictures that spacecraft have taken of near-Earth asteroids. You can see we know actually quite a bit about what their surfaces look like in detail. And that tells us something about how these asteroids formed and where they came from, and maybe about the origin of life on Earth and so on. Those are science investigations, but also planetary defense is important. And this figure in the middle in the bottom is, that's a picture from a security camera in the Russian city of Chelyabinsk. It was taken in the year 2013 when an asteroid entered the atmosphere over the city and exploded. You probably saw a lot of YouTube videos of this. It was very impressive and created an awful lot of damage in that city. And it would be useful for planetary defense reasons to know what are asteroids made out of so that we can prepare for impacts. Okay, so there's sort of a spectrum of how to characterize NEAs, near-Earth asteroids. On the one end of the spectrum, which I've laid out here horizontally, is a spacecraft kind of study. This could be an encounter or an orbit or even a sample return. These provide very rich data. They are extremely expensive, hundreds of millions of dollars, and are only really a very small number of targets are accessible, maybe 2 or 3 or 4, some number like that, can really be accessed through with this kind of study. On the other end of the spectrum is sort of traditional ground-based observing, where you might use spectroscopy to determine compositions. You might measure light curves to tell you something about the shapes, and so on. These are relatively poor data of unresolved bodies. They are relatively cheap. You need a few hours of ground-based telescope time, and you can observe many targets this way. And so this is this continuum from the richest, rarest, most expensive spacecraft observations to the sort of most accessible ground-based observations. And the question is there something in the middle that could be an interesting niche to study asteroids? And of course, the answer is yes, because otherwise I wouldn't be giving you this talk. So I want to just briefly talk about Speckle observations. As a reminder, if you don't think much about Speckle very often, the observations are made at something like 60 hertz, so 60 frames per second. This has the effect of freezing out the atmosphere, so the atmospheric turbulence basically is non-existent in each one of those short exposures. And consequently, we obtain diffraction-limited observations with an 8-meter telescope. Well, that's pretty nice. So Gemini has 2 Speckle cameras. There's Alopeke in the north and Zoro in the south. Each of these provides something like 20 milli-arcsecond angular resolution at that diffraction limit. At the 2 wavelengths that we observe simultaneously, 562 and 832 nanometers, which is kind of like R band and I band. So again, those are observed simultaneously. Given Nyquist sampling, you would say we could resolve bodies that are larger than something like 50 milli-arcseconds with this technique. And finally, these are highly time-constrained observations. The window of observability is really usually only a few hours. What we're doing is we're observing an asteroid as it flies by the Earth, and there's a few-hour window where the object is, the angular size is larger than this sort of 50 milli-arcsecond, where we think we can resolve the body with a Gemini Speckle observation. And I want to specifically give thanks to Ricardo Salinas from Gemini South, who has really mastered this project for us and just made it happen. So thank you, Ricardo. Okay, so here's the summary. At 50 milli-arcseconds or greater, any near-Earth asteroids encounter the Earth something like between 0 and 2 times per year on average. So, excuse me, this is not a particularly rare nor particularly common. So it's right in the middle of that continuum I talked about before. In 2021, we began a campaign to use the Gemini Speckle cameras to obtain multi-wavelength, so 2 channels simultaneously, disk-resolved images of close approaching NEOs. So again, the difference here compared to other campaigns that we resolved NEO, and that allows us 2 different science goals here. We can directly measure the size and shape and albedo of the objects. And importantly, we can look for longitudinal color variations. So as the asteroid NEA is rotating as it flies by the Earth, we can use our 2-channel imaging to see if there's a color change across the surface. This part is red and this part is blue. And this has been predicted from mechanical strength modeling of asteroids, but has never really been observed, or it's hard to observe. So this is a unique opportunity to really understand the evolution, the structure and evolution of NEAs using a ground-based telescope. We have a decent sample size, because we have 0 to 2 objects per year, and detailed characterization at a relatively low cost. We're talking about really a few hours per year to do this work. There have been no technical issues, despite some concerns we had, including very large rates of motion on the sky of these objects as they fly by the Earth. We are using the 512 by 512 array readout to keep our object on the detector. Let's see. Oh, I messed it up. There we go. Okay. So let me show you some preliminary results. Please note at the bottom here, it says preliminary results. Please do not circulate. We're working on our paper, but I don't want to let anything out quite yet. The first object we observed is an asteroid called Eros, asteroid 433 Eros. It's the largest NEO. Actually, it was the first discovered NEA, excuse me, and the first discovered NEA discovered in 1898. It turns out, just by coincidence, this was the first one available as we began our campaign, and this is an excellent calibration or test or validation target because it was intensively studied by NASA's NEAR mission, which orbited about 20 years ago, orbited this asteroid. So we have excellent data that we can compare to our new Gemini observations. Excuse me. The expected size was about 68 milliarc seconds, so just really a little bit bigger than this threshold that we set out, and observations were made in June of 21. Okay, so these are not the Gemini data yet. Let me just show you our predictions first. So this is let me walk you through what we're looking at here. Again, we know quite a bit about Eros because of the NASA mission. And so on the top row, those 3 images on the top row, is how Eros would look at its maximum elongation, which happened to be during June of 21 when it flew by. And the bottom row is how Eros would look during its minimum elongation if it was oriented a different way, which was a few months later. In the far left row is our spacecraft data from like 1,000 kilometers from the asteroid. So really close, excellent data, like you would make a geological map out of it. The middle row, sorry, excuse me, the middle column, the far left column is our excellent data. The middle column is somewhat degraded. And then the right column is degraded to the resolution that we would expect the asteroid would look like to the Gemini Speckle cameras. So I put this pink box in the upper right because that's the thing we expected to see in June of 21. Excuse me. Okay, so here's our data. On the left of these 2 images I'm showing is the 562 nanometers. Again, it's like R band. And the right one is 832 nanometers like I band. The full image is shown there with the 1 arcsecond scale bar. And then I have a little blow up. I don't know if you can see my mouse, but anyways, a little excerpted where you can see the image better. And it works. It's not surprising. Gemini is an excellent facility. The cameras work just as advertised, and we know the asteroid quite well, but it still is very reassuring to have a, excuse me, a confirmation of our approach as we proceed. Okay, on to our second target. We observed asteroid 7482 in January of 2022. The predicted angular size excuse me, was 120 milliarc seconds. so quite a bit bigger than this 50 milliarcsecond threshold. This asteroid has a known 2.6 hour rotation period. And so we observed for 3 hours in order to get a full rotation to look for this color change as a function of the rotation. These images here are only in the 832, excuse me, wavelength. And again, the 1 arcsecond scale bar is there. The red core here is similar to what I showed you before. That's what you should be looking at here. And you can see that there is a rotation as a function of time. We are resolving this body and seeing it rotate. Future work that we need to do is to compare this 832 data to the R-band data, and again, look for these color changes. We have quite a bit of other data on this asteroid from other telescopes. We're going to combine it all to do a really sort of comprehensive study of this particular object. Okay, and then here's one more. Results to come, asteroid 7335. We observed this one on May 26, Gemini South. The predicted angular size was about 90 milliarcseconds, so intermediate between the first one and the second one I showed you. We haven't finished our data analysis here, so you have to stay tuned, but it's going to be good. And finally, I want to advertise a future opportunity, actually. Asteroid Apophis will pass by the Earth in 2029. This is, you may have heard of this asteroid. It's a very famous one because it will come so close to the Earth. The angular size at closest approach is going to be something like 440 milliarcseconds, so like almost half an arcsecond. And this is something like 20 resolution elements across the disk. So this is far and away the best opportunity of any asteroid as it flies by the Earth. This is a fabulous apparition. NASA's OSIRIS-APEX mission, it was recently announced, is going to have an encounter actually to orbit this asteroid shortly after the asteroid flies by the Earth. So first the asteroid goes by the Earth, and then a matter of days later, the NASA spacecraft will catch up and start its orbiting mission around the asteroid. And of course, the mission is going to produce incredible data that far exceeds what we can do with any ground-based telescope. But those are after the Earth encounter. And so the sensible and scientifically interesting thing to do is to observe this Apophis asteroid before it flies by the Earth, and then also again after, and then we can use the NASA spacecraft again to sort of anchor our studies. But the real trick there will be to ask, did some properties of the asteroid and its surface change before and after the Earth encounter? And again, there are models that say that it will, and we can test those models with Gemini and the Speckle cameras. Finally, just to show you this picture in the bottom right, this is the same one before as Eros, and I had that middle column where I said the sort of intermediate resolution. Again, the right column is what we saw for Eros, and the left column is like perfect spacecraft data. The middle column is what we're going to see for Apophis. So we're going to have this kind of excellent data with Gemini and the Speckle cameras in 2029. Okay, so in summary, we've demonstrated that speckle imaging is a powerful and unique NEA characterization tool. I apologize, that should say NEA instead of NEO on the slide. Same thing. Those are near-Earth asteroids. We've observed Eros, we've observed 7482. Next week was when we sort of expect to get back to our processing of 7335. So again, a small sample that we've accumulated, but I think is going to be extremely powerful, and to demonstrate this technique, which has not been used before, and place us in an interesting spot in this continuum of studying asteroids. There are more targets coming, although actually for the next 12 months, there's none. And so it's a good time for us to write the paper and get it out, and we'll come back to this, sort of second wave sometime next year. And the sweet spot, or the best targets for us, are close approaching asteroids that are not spacecraft targets. And finally, as I mentioned, Apophis, which is coming in 2029, is going to be a fabulous, very unusual, fabulous apparition and opportunity. Thank you for your time. That's the end of my talk. I believe I'll be in the Slack and can address questions there. And if there are questions here that we can do in real time, I'm good with that too. Thank you. very
All
much.
right. Thank you, David, for your talk. Are there any questions? If you're in the room, you can come up to a mic.
I'll
Yeah.
ask the first question. Hi, thanks for the great talk. This is Hui-Han Kim at Gemini. One of the example you showed, like 7482, I believe, and the 832 nanometer images, I see some diffuse feature around the actual object. Is it real or is just some kind of artifact after post-processing?
Yeah, it's not. It's a good question. I didn't want to talk about it too much because
Sorry.
no, it's a very good question. It's it's part of the black magic of Speckle observing and reductions, which I am not an expert in. I'm working with people who know a lot about that. The diffuse background, I think, is not a real signature from this asteroid. And the question is, what is the core that you believe, and what is the diffuse background that you don't believe, and where does that transition change? And that actually is the main thing we're working on right now to finish this paper. So it's an excellent question. And I think we know how to define that, but we need to really make sure we've got it sort of uniformly applied across all of our data. So thanks for that. It's a perfect question.
Okay, thank you.
Go ahead.
Hi, David. This is Ricardo Salinas. Is there any future NEO that's going to be visible from both Gemini North and South, so we can do simultaneous observations with Alopec and Sorrow 4 filters all the way?
Wow.
Do you have anyone in mind already or not?
Yeah. So I didn't know Ricardo was there. Make sure you go shake his hand because he's the one who makes all this happen. Thank you, Ricardo.
Thank you.
I have not investigated that. As I said, we have a 1 year period where just by coincidence there's no good targets coming, so we're kind of on hold. After that, I have the answer on my computer, but I can't tell you offhand. So let me send you a message separately, and we can look at that.
Are there any questions on the Slack?
Yeah. Hey, David, this is Zach. Tom Speckle, another science fellow at Gemini Earth, has a question saying, is it possible to observe the pixel-to-pixel color variation in a single pair of frames in different bands, or do you only get the disk integrated color as a function of rotation?
So the goal is to do, I don't know if I would say pixel by pixel, but let's say resolution element by resolution element. Basically what you do, you just take a ratio of the two images as a function of time, and you look to see if color blobs are moving across the surface in a coherent way. It's a little bit hard to be rigorous about that because it turns into color blobs. And so we have some idea, again, from Eros, we know what the colors across that surface actually are. And so I think we can back out our sensitivity to color changes. For the other ones, it might be a little bit tricky to actually, say, if we don't detect blobs that we really believe, well, can we put a limit on that? That is some work that we need to do. And actually, one of the geologists on our team is going to be doing that. And he is. It's pretty fun that we're doing asteroid geology with a telescope. Everybody should just think about that for a moment. Thanks, Tom, for that question. Thanks, Zach.